Then we'll give a talk on some kind of strong regular graphs. This family of graphs is one on the top of this workshop.
Okay. Do you see my slides?
Yeah, everything is fine. Yeah.
Yeah. If you want me to shall I go to full screen or in this
would be
way?
Nice. Yeah. If you can, yeah, it would be nice.
Yeah, okay. Yeah. Yeah.
Good.
Yeah.
Very nice. Thank you.
Thanks. Okay. Yeah, I would like first to thank the organizers for organizing this workshop and also for inviting me to give a talk here. So I will give a talk of q-ary strongly regular graphs, and this is joint work with Michael Braun and Vedran and Andrea from my colleagues from my department. Okay. And first, I will start with basic definitions. With definition of t-design. So t-design with parameters vk lambda is a finite instance structure with v points, and every block is incident with k points, and every t elements of every t points are incident with exactly lambda blocks. It is so very important case is when number of blocks is equal to number of points, and in that case we call design symmetric. It is well known that when design is symmetric, then t is at most 2 then. And what is so it is also very well known that if we have a t design, then this design is also s design for s between 0 and t, and that is actually important for our construction here. And of course, I will be talking about some kind of strongly regular graph. So, and this is the definition of strongly regular graph. I don't think that I have to actually repeat this definition. So it is strongly regular graphs were introduced by Bose in 1963, and we all know what it is. So we have v points, every point v vertices, every vertex is of degree k, and number of common neighbors of two vertices depend on the fact that if the vertices are adjacent or not. So we have lambda or mu common neighbors. It is also very well known that this is a connection between strongly regular graphs and symmetric designs. So whenever we have a strongly regular graph, when lambda is equal to mu, then its adjacency matrix is actually the incidence matrix of a symmetric wiki lambda design. And if we have this relation that mu is equal to lambda plus 2, then we add a diagonal. So we add loops actually at each vertex, and in that case, the adjacency matrix become incidence matrix of symmetric design with parameters vk plus 1, lambda plus 2. And we can go in other direction too. So this is a well-known connection between strongly regular graphs with these specific parameters and symmetric designs. I will need this definition of paired orbits or self-paired orbit. So if we have a group G acting transitively on set omega, and we have any element from this set omega, and we take an orbit of a stabilizer of that element alpha, then we can define, or we define this delta prime in this way, that this is a set of all elements alpha G, such that G goes through all group, and that alpha, that alpha times inverse of G is in delta. In that case, it is known that we also get an orbit of stabilizer. And these two orbits, delta and delta prime, are called paired orbits. And if it is possible also that delta is equal to delta prime, in that case, we call that orbit of stabilizer self-paired. Okay, so this is a theorem by Jenny Key and Jamshid Nouri from I'm not sure, it is first decade of this century, maybe 2003, I think. So we have a finite permutation group G, which is primitive, acting on a set omega of size n, and we have alpha from that set omega, which is not that, and we have a delta, which is orbit of stabilizer, but we exclude this case that that the delta is equal is singleton, just to avoid this trivial situation. Then we make a set B in that way that we actually form a development of this delta, of this capital delta. And we also form this set of set E of what will be actually edges of a graph. So these are images of this set alpha delta, where delta is from the set capital delta, and we also take all images when we act by all the elements of G. In that case, design incident structure with point set omega and the block set B is a symmetric one design. And if this delta is self-paired orbit of stabilizer G alpha, then we obtain a regular connected graph with the valency cardinality of delta. And in that case, this design is self-dual. And in both cases, G acts as an automorphism group on these structures, primitively on the vertices of the graph and on the points and blocks of design. So in this case, we can construct primitive one designs and the regular graphs. And what is important, at the beginning I said that every T design is actually S design for S smaller than T, and that means that if we want to construct all T designs, actually all the candidates are one design. So in that way we construct all the candidates for T designs, because one design it's not very exciting structure. We are always looking for T designs with T greater than 1. Okay, and of course we get regular design. Of course, it is interesting if this regular graph. It is interesting if this graph is not just regular, then yeah, of course, if it is, for example, strongly regular. More. In this theorem of Jenny Key and Jamshid Nouri, instead of taking one orbit, we can always take a union of orbits, and we also get to one design. Moreover, in that way, we can obtain all one designs with all primitive one designs, but all primitive symmetric one designs, but not actually all of them, just those that have a conjugate stabilizer of point and block. So whenever we have that such a situation, we can apply theorem by Jenny and Jamshid and obtain such a design. Then we generalize this construction in order to this construction enables us to construct all two designs that are not necessarily symmetric. So we also, again, we have a permutation group G. In this case, it does not have to be primitive. So we're acting transitively on two sets, omega 1 and omega 2 of sizes m and n respectively. And we take one element alpha from gamma 1, and we define the set delta 2 to be union of these orbits of stabilizer of alpha. So we can assume that delta 1, small delta 1 to delta s are represented for distinct orbits of the stabilizer. In that case, we also can define this set B, which is kind of development of this set delta 2. And we obtain incident structure, which is one design. In our case, it is not necessarily symmetric. Yeah, okay. And this is number of blocks is given here. And these quotient groups, X and automorphism group of that design transitively on points and blocks. Quotient is here just to ensure that the action is faithful. And moreover, if we have group G acting transitively on points and blocks of one design, let's call that design D, then that one design can be obtained as described in theorem 2. So this is actually characterization of one design admitting a transitive action of some group on points and blocks. We can, this is a way how we can look at that design from the previous theorem. So we can say that point set is omega 2 and the block set is omega 1, and the block this block alpha G prime is incident with the points that are given here. So this is it may be useful to know this fact about that design when you think about this construction. And as I said before, when we want to construct, if we want to construct the designs, so we can construct all one designs and then check which design is from our set of designs, that set of one designs that we obtained is two design. For example, we constructed actually a large number of two designs and three designs from some linear, unitary, symplectic, orthogonal, and some sporadic group too. So this construction seemed to be fruitful in that way. Of course, if you pick the right group, some groups are give more results, some groups less. And we have this corollary, which gives this connection between these designs and graphs. If these sets omega 1 and omega 2 are equal, and if this delta 2 is union of self-paired and mutually paired orbits of the stabilizer, then the incidence matrix of that one design that we obtained is actually a JCC matrix of regular graph. And yeah, this is the way how we can think about that graph. So set of vertices is omega 1, which is equal to omega 2, and the vertex alpha G prime is incident with this set of vertices. Yeah. And again, in this way, we can obtain all regular graphs that can be constructed from some group, and some of them can have some more can be also, for example, strongly regular, and in that way we constructed also a bunch of strongly regular graphs, for example, and we're lucky. Actually, Andrea constructed using this U42 constructed strongly regular graphs with parameters 216, 44, 8, and 540, 187, 58, 60, which actually were the first strongly regular graphs with these parameters, first examples of strongly regular graphs with these parameters. And she used this group, unitary group 4.2, which is very fruitful for this construction. Okay. It is also possible to have this connection with codes. So codes here will be linear codes, which means that codes will be k-dimensional subspaces of some of a vector space over a field of order Q, and a linear code with parameters n, k, and d is a linear code n. N is that n here, and so we have vector space fqn, and k is a dimension of this code, and d is a minimum distance, where this is just a minimum Hamming distance between two code words. And this parameter d is very important because this parameter d gives us error correcting capacity of the code. An automorphism of code is any permutation of coordinate position that maps code word to code word. And what is important here, if we take instance matrix of a design or adjacency matrix of a graph, and then we span a code, automorphism group of a code will be this automorphism group of a design or a graph will be a subgroup of automorphism group of the code. So in that way, if we start with large, which with design or a graph with a large automorphism group, then we can construct codes with the large automorphism groups. Yeah, which is important for one kind of decoding, which is called permutation decoding, developed by McWilliams in 1964. What is that? So any linear code is isomorphic to code with generative matrix in the so-called standard form. So this is that form. So first we have first part is identity matrix of order k, and then we have some matrix A. First k coordinate positions are information symbols, and the other coordinate positions are check symbols. So in this permutation decoding, we need something which is called PD set, and this is definition. So we have t error correcting code with information set I and check set C. Then a PD set of that code is set S of automorphism of the code with this property that every t set of coordinate position is moved by at least one permutation from S into the check position C, which means that using this permutations from S, we can move error from that information set. Unfortunately, this property of having PD set is not invariant under isomorphism. So so this is unfortunate case, and there is a lower bound for this cardinality of S, which is given here. This is well-known Gordon bound, and that's why good candidates for permutation decoding are linear codes with large automorphism group and small dimension. And using, so that's why it is that's why using this theorem we can construct designs or graphs and with large automorphism groups. And then we can span code with instance matrices or adjacency matrices and get some codes which are good candidates for this permutation decoding. So I said that I will talk about Q analogs of strongly regular graphs. So first I will say something about Q analogs of designs. So Q analogs of designs were introduced by Dersat in 1976. In general, a Q analog of some statement, which depends on variable Q, is some statement that generalizes the node statement, and to that statement, this generalized statement reduces when we have that limit when Q goes to 1. And in combinatorial setting, it is usually we have this Q analog when we replace sets and subsets with the vector spaces and with the vector space and its subspaces. And this is the way how Delsart defined Q analogs of designs. So we have a vector space of dimension V over a finite field Q, and we have some K subspaces and a simple design with parameters T, V, K, and lambda Q. Q is for this order of finite field. So subspace design with these parameters is actually set of K subspaces such that each T subspace of that vector space is contained in exactly lambda blocks. And the subspace designs also have many other names, so Q analogs of designs, or q-ary designs, or designs for final fields, or designs in vector spaces, or designs in a Q Johnson scheme, or geometric designs, and so on. Q designs. So all these are names for this same structure introduced by Delsart. In 1987, Thomas constructed first non-trivial Q analog of design with parameters 2 and 372 when n is greater than 6 and n is equal to 6 times k plus 1 or n is 6 k minus 1. And then Suzuki in 1992 constructed the designs with these parameters, so n is also equal to 6k plus 1 or 6k minus 1. So you can see that designs, the parameters of designs constructed by Thomas are just these parameters when q is equal to. So this is actually generalization. And then Miyakawa, Akihiro Munewasa, and Yoshihara in 1995 gave a classification of two designs for which n is equal 6 or 7 and q is equal 2 or 3. K is 3, having an automorphism group that acts transitively on the point set. And recently we have a very important result in that area. So Michael Braun, Tuvi Etzion, Estergaard, and Bardi, and Alfred Wasserman published this paper, Existence of Q Analogs of Steiner Systems. So this is actually the first example of Q analog of Steiner design that does not arise from spreads. So these are actually, it is still not known if Q analog of Fano plane exists. It is known that if it does exist, then automorphism group is very small. And yeah. So we gave this this generalization of our theorem that I gave before, and this generalization that can be applied to Q designs, to subspace designs. So we have G, which is a subgroup of general linear group acting transitively. So if this G acts transitive in a set of 1 subspaces, and then we get some subgroup P and form delta in this way for distinct 1 subspaces delta 1 to delta S, then we form a set of blocks in the same way that we did it for ordinary designs. And in that way, we get Q analog of one design with these parameters. And the group G acts as an automorphism group of the constructed Q analog design and transitively of the one spaces of the vector space and on the set of blocks of the this subspace design, the subspace one design. Again, this is a characterization of such designs. So if you have a subspace design with the group G acting transitively on one spaces and on the blocks, then we can obtain this design using this theorem above. So example first, single group acts an automorphism group on of a point hyperplane design, and we can actually look at this design as Q analog of design, which is but this is actually trivial subspace design. So, but this is just to show that we can it is possible to apply this theorem and to get something. So if you look at this point hyperplane design as a Q design, as a subspace design, then this is a trivial case actually. And we check these small groups, GL32, GL42, and so on, and we didn't find two design, transitive subspace two design in this, yeah. But if we, of course, we got some one designs, and so this is a list of one designs. But what we can do, we can actually using these designs, we can maybe combine some one designs. So we can make union of block sets of one designs and maybe get some subspace two design with a group which acts transitively on one subspaces, but not transitively on blocks. Yeah, and so we did it for this case when V is equal to 7, so Q is 2 and K is equal to 3. So we combine some of these one designs, and we obtain we combine some M designs when one designs where M is between 2 and 15, and we obtained some two designs, but just I have to note that that these designs are not new. So all these designs actually were constructed and classified in this paper by Miyakawa and Akihiro Monemasa and Yoshihara. So these are not new designs, but just constructed. This is just example that they can be constructed using this theorem, and then so one designs are constructed using these theorems, and then we can combine these one designs and obtain two designs. And of course, in similar way, so that famous Steiner Q design with parameters 2, 13, 3, 1, 2, constructed by Michael Braun and all the others, admit the normalizer of a single group of GL13-2 as an automorphism group, which acts transitively on one spaces, but acts in 15 orbits on the blocks. So we can actually construct 15 of these one designs and combine these 15 one designs, and again construct that. Actually, it is not one Q design. It's actually they constructed actually a lot of these examples with these parameters, so we can obtain these examples also using that theorem 3 that way. Yeah. But the title of my talk was Q analogs of SRGs or something like that. So recently in this preprint, we defined Q analogs of graphs, and especially Q analogs of strongly regular graphs. So let me tell you how we did it. So we define a Q analog of a graph as just a subset of some of possessing of some two subspaces. So this is analog of a simple graph when the edges are just subsets, two subsets, and the neighborhood of some one subspace is defined to be union of all the edges containing that one subset X. So union. And then we say that q-ary graph is called regular if actually these neighborhoods, which are defined as unions of edges, are actually for all we can say vertices, all one subspaces, these neighborhoods are actually subspaces of dimension k+1. And we say that regular graph is strongly regular if with parameters vk lambda mu, if all the neighborhoods are of are subspaces of dimension k+1, and we have the following condition. So for all the vertices y and z, the number of vertices one subspaces, okay, to be precise, the number of one subspace is x, such that this sum x plus y is an edge and x plus z is an edge. So the number of such vertices or such one subspaces x is lambda if y plus z is an edge, or mu otherwise. So this is now we're talking a lot about this generalization. So this is something that after a lot of thinking, we thought that this is the right way to generalize a strongly regular graph to that subspace case. So to generalize it to vector spaces. Of course, if this is a right generalization, so we need some properties of that generalization, which reminds us to properties of ordinary strongly regular graphs. So for the parameters of a strongly regular graph with parameters vk lambda mu and q, which is order of the field, the following condition holds. And what is important, when we have this limit where q goes to 1, then we obtain this well-known formula for the parameters of strongly regular graphs, so vk lambda mu. So this is something that convinces that this is not this is one thing that convinces that this is a right way to generalize a strongly regular graph to the vector spaces. Okay. Next thing that we were interested in is if so we know that complete graph in that ordinary, when we define ordinary strongly regular graph, that complete graph is strongly regular. And so we were thinking, yes, that also complete graph in this case should be strongly regular. So if we take all two subspaces, then so we thought that it also should be q-ary strongly regular graph. So the complete graph, when we take all these two subspaces, is actually strongly regular graph with these parameters. And this is the q analog of the complete graph, as I said, which is strongly regular graph with these parameters v minus 1, v minus 2, 0. So yeah, that was we're happy when we noticed that. Then that this is behaving as we want it actually. Yeah, but we wanted also some non-trivial example. So this is a non-trivial example of a strongly regular graph. So this we constructed it, this graph with parameters 4, 2, 1, 3, 2. So this last 2 is actually means that we're working over a binary field. Okay, so we have points, or yeah, okay, should be vertices, not points. So one subspace is we have these 15 one subspaces, and okay, from x1 to x15, and then we form these 15 blocks, or actually, yeah, okay, 15 subspaces E1 to E15. These are all 2 subspaces, and then we checked, and actually, if you take this 15 two subsets as edges, you obtain a strongly regular graph with these parameters. Now, and I can tell you that it is not easy to find such a structure. Also we're satisfied with that, because it should not be so easy to find. So that also convinces that maybe our definition is okay. We also have we know that that connection between the symmetric designs actually and strongly regular graphs from the beginning of my talk. We also wanted to know if there is some connection between this old definition of Belsart of Q analog of design and this Q analog of strongly regular graph that we constructed. So, and there is. So if we have a strongly regular q-ary graph with these parameters, v, k, lambda, lambda plus 2q, then the set of neighbors, this set of neighborhoods, actual set of neighborhoods, is actually to q-ary design with these parameters 2, q, 2, v, k plus 1, lambda plus 2q. So this is also something that we wanted to obtain, because because if we have this connection between strongly regular graphs and some strongly regular graphs and some designs, then we wanted also connection between some q-ary designs and some strongly regular graphs, and this is a connection. So yeah, we were satisfied with that. I hope that I can convince you also that this is a good way to generalize definition of strongly regular graph to that to vector spaces. And again, so in that theorem that I showed previously for construction of one designs from group ordinary one designs. So we said that in some cases, actually we construct a regular graph. So the same situation is here. So taking the same construction with this extra condition, actually we obtain something which is a set of spaces of neighbors, so set of neighborhoods which are then which has to be subspaces of a regular Q graph. Okay, so we also have this this connection with the construction. And there is also a connection between these things that that I showed you previously and the subspace codes. So what is subspace code? There is just subspace codes are just a bunch of some subspaces ambiental vector space. Subspace codes are used in random network coding, and so there are a lot of research recently about subspace codes because of that connection. And special case of subspace codes is when all these subspaces are of the same dimension. Then these codes are called, such codes are called constant dimension codes. So all these subspaces, which are in this case code words, have the same dimension. And also a special class of constant dimension codes are orbit codes. And the orbit codes are defined as orbits of some subgroup of a general linear group. And it is easy to see that applying that theorem, one obtained, it's not theorem 3 and 4. Okay, I messed up with these numbers. So these, this is theorem and corollary. Yeah, so this, yeah, okay, it is corollary 4. Yeah. Okay, so using that previous theorem and this corollary, we can obtain orbit code. So, which is obviously interesting for people that are working in subspace codes. And okay, so now when we have a definition of strongly regular q-ary graph, then also we can develop some generalizations that are, so one of generalizations that is probably will cross your mind, yeah, especially many of you that are interested in the graphs. Of course, if we can also have this definition of the graph in this way. So if we again have a regular q-ary graph and these number of for two subspaces y and z, the number of one subspace is x, such that x plus y is an edge and x plus z is an edge. Also can take just two values, a and b. Okay, then we can, in that way, we can say that that this is a q-ary graph, and we can try. So we didn't do much here in this case, but of course it is possible to see if these graphs defined in this way also have some similar properties that the graphs in that ordinary case have. Okay, so actually that's all that I wanted to say. Thank you.
Okay, thank you very much for the interesting talk. Are there any questions coming to Dean?
Yes, I can.
Yeah, sure, please. Yeah, sure, please.
Yeah, are there circulant q-ary strongly regular graph in the sense that the single group acts transitively on the set of vertices?
I don't know, actually. I don't know. So as I said, it is not. It was not easy to find such a structure in. So
I guess the symplectic polar graph could be considered as a q-ary strongly regular graph.
Mm-hmm.
It is a strongly regular graph in the usual sense.
Yeah, yeah.
And the set of vertices is just the set of one subspaces of a even dimensional vector space, and edges are just totally isotropic lines. And I don't know, it is, I think, irregular in your sense, but I don't know if it satisfies the additional property of being strongly regular, but that would be a good candidate. But I don't think it leads to a true design, true analog of two designs though.
Yeah, thank you. We didn't think about that. Yeah, but certainly interesting observation. Yeah, thanks.
Yeah, thank you for interesting talk.
Yeah, thank you.
Mention my very old work.
Yeah, okay, yeah, but it's important. Yeah, thank you.
Is any other questions today? Yeah, Martin, please.
Yeah, maybe a bit along the same line. You showed this example of a q-ary graph on 15 vertices.
Yeah.
And in your slides, and I was wondering, yeah, well, this one. So, does it correspond to the symplectic variety or not? That was what I was wondering. I mean,
I don't remember now. I know that we were recently talking with Francesco, who visited us, Francesco Pavese, who visited us recently, and we were talking about this example in this case of the setting of projective geometry, but actually I don't remember now when. Yeah.
I mean, the first thing to me is that the parameters check out. So I mean, it is a bunch of lines, and if you have two points on an isotropic line, then there will be one neighbor, which is and lambda is 1, so that works. But it could be non-isomorphic, probably. So it could also be, of course, but I'm not sure.
Yeah, and Francesco seen some geometric property of that, and of course, and he was actually thinking about generalization of that, but yeah, I don't remember actually in which setting it was. Yeah.
Okay.
As far as I remember, no, it was not isomorphic because the last parameter mu was missing. So I think it was not.
Okay, thank you.
But we can check.
Yeah,
okay,
thanks, Andrea. Yeah. I forgot that. Yeah.
Okay, other questions to Dean? Well, I'm just wondering, did you consider any examples of q-ary graphs?
No, we still didn't. Yeah, we still didn't. But this is just yeah, obvious generalization, and we still didn't have time to investigate that. But yeah, it's obvious direction to further research, I think, here.
I see. Okay. Thank you. Any other questions? Well, if not, then let us thank Dean again for this very interesting and useful talk, containing a lot of new generalizations for strong irregular graphs and other kind of regular graphs. Thank you very much. Thank you.
Thank you, Elena.
Yeah.